Well, thanks very much for the talk slot today. I'm sorry that Jess Work couldn't make it. But today I'm just going to give you a few of the science highlights from a recent survey that I've conducted with my collaborators, which are credited at the bottom of the slide here. And what we've been trying to do is find the most metal-poor clouds of gas at redshift 3. And we've had a number of science goals that have come from this. So just to give you an idea of the timeline of events that we're looking at here in the early universe. So at some high redshift, the first stars formed. These stars were very massive, or thought to be very massive, and so lived relatively short lives. And at the moment, they're thought to have died as type 2 supernovae explosions. And it's these supernovae explosions that produce the first dosage of metals to the surrounding medium. Apart from enriching the surrounding medium, it also heated the surrounding medium, of course, as well. And this hot and enriched gas would have eventually cooled and condensed to some cloud of gas, which then later condensed further into the second generation of stars, such as those that we see around the halo of our galaxy today. And so what I want to draw your attention to today is this intermediary between the explosions of the first stars and their products incorporation into the second generation of stars, namely this cloud of gas, which presumably must exist somewhere in the universe, probably at some high redshift. And what I'm going to propose is that you can search for these clouds of gas by looking for their absorption signatures against a bright background quasar. And so presumably this is some cloud of near pristine cold gas. And what I'm arguing here is that they're in fact a subset of the Damped Lyman-alpha systems, namely the most metal-poor Damped Lyman-alpha systems. So we all know what DLAs are. They're essentially large reservoirs of neutral hydrogen gas which exhibit these Lorentzian damping wings, which are easily discernible from the Lyman-alpha forest. Typically, they have metallicities which are about 1/30th of solar or thereabouts, 10th to 1/30th of solar. What I'm interested in is finding everything below 100th of solar. So everything below here in the tail of this metallicity distribution. So they're very rare, but very rich if you can find them. And so we conducted a survey to find these things, including some that came from the literature. We found about 20 DLAs, 20 different galaxies, that have a metallicity distribution which goes right down to 1/3000th of solar. So these things really are near pristine, some of them. So today I'm going to tell you just some of the science highlights that have come from this survey, just a flavor of what we've done. If you're interested in other things, by all means come and chat to me later. Let me start by talking about the oxygen problem. So this is something that's been known about for about 3 decades or so. And that is that the oxygen to iron ratio, very roughly, is monotonic relationship really between oxygen to iron and the progenitor mass of a type 2 supernova, of a massive star. And so you can think about this, that the oxygen to iron ratio is telling you something about the IMF. In a broad sense, modulo the energy by which the type 2 supernovae exploded. So the oxygen problem is this. I mean, this has been known for 30 years or so. There are 4 ways that you can measure the oxygen abundance in the most metal-poor stars. Okay, you want to go down to the lowest metallicities because this is the regime where just type 2 supernovae are contributing to the enrichment. So 4 diagnostics, and none of them agree at the lowest metallicities. None of them mutually agree, right? What's thought to be the most accurate is this green line, this forbidden 01 6300 angstrom line. But the problem is this is very weak at the lowest metallicity, and so you don't really get a good handle on what the oxygen abundance is in these low metallicity stars. So we decided to attack this with these galaxies, these DLA galaxies. And what I've shown here is the open symbols show the what you see from this forbidden 01 6300 angstrom line in stars. And what I've plotted are these red triangles, which are the DLAs, the metal-poor DLAs. So for 20 different DLA galaxies, 20 different galaxies, what you're seeing is that there's very little spread in the oxygen to iron ratio. So all of these DLAs are seeing the same IMF worth of the same stars that exploded with the same energy. unless you can think of a more contrived scenario by which you can produce this result. Something that's interesting is as you push to the lowest metallicities, there seems to be a deviation from this trend. Namely, there could potentially be a rise in the oxygen to iron ratio at the lowest metallicities. And this, as far as I can think of, there's 3 exciting explanations. All of them are great. So namely, one, you could push down to lower metallicities and your nucleosynthesis may be changing, i.e. we may be starting to see the nucleosynthetic products from just the first few generations of stars. The other possibility is that the energy by which those stars exploded may be different from what we see in the local universe. Or the IMF is changing at the lowest metallicities and is becoming more bottom light. So those are the 3 possibilities I can think of, but all exciting. We've recently almost doubled this sample at the lowest metallicities, and this trend seems to hold true. So stay tuned for this. I might skip over these 2 interesting systems. The punchline is that they appear to show very different nucleosynthetic products from all the other DLAs in our sample. And we've concluded that these systems, which are amongst our lowest metallicity systems, may very well have been enriched by just the first generation of stars or just a few generations of early stars. If you're interested, come and talk to me later. For now, I'll just tell you what you can, one of the properties that you can measure from these low metallicity DLAs. So when these metals were originally formed in these massive stars, the iron peak elements were formed in the center. And it's in the center of these massive stars that drives the explosion of the type 2 supernovae. So the ratio of the iron peak elements is very sensitive to the explosion physics. So their ratio can tell you something about the energy that was released from these type 2 supernovae explosions. So what I've shown here is that these are low energy type 2 supernovae. The blue is for typical, and green is going higher, and then hypernovae is the red one, is the red contours. And if you believe the models and the data, then the data and the models are telling us that the energy that was released from these early stars must have been relatively low compared to what we see in the local universe today. So Joel's asked me to include something about primordial nucleosynthesis. This is stuff that will appear on AstroPH postings tonight, somewhere in the middle. So what I'm going to tell you about now is this recent survey where we've used the most metal-poor damped Lyman-alpha systems to place a limit on primordial nucleosynthesis. Now, the reason is that we can do this is because these systems have barely seen a metal, and they still contain the products from Big Bang nucleosynthesis. And what I'm arguing is that DLAs are potentially the best environments where you can measure the primordial deuterium abundance. And the reason is twofold, which I'll show. All you need to do is accurately measure the H1 column density and accurately measure the D1 column density, the deuterium column density. If you do that, then you can get a precise measure of the deuterium abundance. And so I'm going to show you the new system that we've just found. This was observed in May with Keck, high res. What you can see here is the damped Lyman-alpha system. As you can see the Lorentzian rings, we get a very good measure of the H1 column density from this system. And here are the Lyman series lines, which is really quite incredible. So what you see here, these red tick marks show you where hydrogen absorption components are, and the green tick marks show you the deuterium absorption components, which is offset by 82 kilometers per second. So what you can see is at Lyman gamma, you can start to see a little bit of resolved deuterium absorption here, and then more deuterium absorption. It becomes even cleaner as you move to Lyman epsilon. In fact, if you look in every single one of these panels, you see a deuterium absorption line in every single one. And I actually ran out of room on the slide here. This actually goes down to Lyman 18. And so we really get a very good measure of the deuterium column density here in this system because we have a range of deuterium lines with a range of oscillator strengths, really pins down this. When you have this in conjunction with the Lyman-alpha line, which gives you these broad wings from where you can get the H1 column density, you can really pin down these values very well. And so this whole idea of trying to measure primordial deuterium in DLAs has led us to try and answer this question, and that is, why is there an excess dispersion in the currently observed D to H systems? So here is a list of the top 10 as of last year. What you can see here is that the quoted values and their quoted errors is much smaller than the observed dispersion in all of these results. And so what we want to know is there any sort of systematics or biases that are affecting these results? And so we've tried to reanalyze all these systems that obey a set of strict criteria and try to understand what the nature of this dispersion is and really pin down what the primordial value is. So we've done a careful modeling of both the continuum and emission lines of the quasar simultaneously with the absorption of the Damped Lyman-alpha system and everything else that goes with it. If you want to come and talk to me about this later, by all means, I'm happy to discuss the details. Something I want to highlight is this blind analysis technique that we adopted. And so this is to remove as much as possible human bias in the results. So the idea is all we see is the quality of the fits, the chi-squared of the fits, and so all we see is whether or not we believe this is a good fit. We don't actually see any other parameters of the fit. The idea being that if any sort of human biases might creep in, then you might bias these measurements one way or the other. And so when we unblind ourselves and we see the final result, that is the result that we publish in the paper. So in order to do this, we were limited by software, so I had to write a new piece of software, which I lovingly called the absorption line software, or Alice. In case you don't know, this is Alice Deason. I'm her husband. The idea of this software is that it simultaneously fits both the emission and absorption lines at the same time. It fits to the ratio of deuterium to hydrogen directly, plus other important features which have enabled this to occur. So we reanalyzed 5 systems, and these are the results from the 5 systems that we reanalyzed for the primordial deuterium abundance. All pretty much self-consistent. And to give you an indication of what this corresponds to in terms of a cosmological parameter, omega baryons, this is for the standard model, this axis. So if you've read the Planck paper, you would know that this is roughly consistent with the 1 and 2 sigma bounds of omega baryons derived from Planck. And so not only are these new measurements of deuterium, this orange one is the one I just showed you. Not only are these measurements of deuterium self-consistent with each other within the errors, but they're also consistent with the standard model that we get from Planck CMB. So just to highlight this further, from BBN, assuming the standard model of nucleosynthesis, standard model of cosmology and particle physics, we get this answer for the baryon density, and the Planck CMB gets this value. So they're both very mutually consistent with each other. So we've also searched for departures from the standard model of cosmology and particle physics. And so what I show on the left here is a joint analysis between the Planck CMB and these BBN results. The D to H results are shown here. There's a degeneracy between the effective number of neutrino species and omega baryons. And what you can see is that the green, which is the Planck CMB, is in very good agreement with the deuterium results. Namely, we can rule out an additional sterile neutrino at almost 3 sigma confidence. The story is slightly different, though, if you combine deuterium with the primordial helium mass fraction, and the red shows the joint analysis of the two. This seems to rule out either 3 or 4 neutrino species. So this is still a matter of concern. The problem is likely due to the helium-4 mass fraction. There's still a bit of uncertainties, systematic uncertainties in measuring these abundances. But if you're interested, come and talk to me more about these details later. So just to give you a quick summary of what I've told you about today. So we conducted a survey to find the most metal-poor clouds of gas in the high redshift universe, redshift 3 or thereabouts. As part of this survey, we addressed the oxygen problem, and that is we now see that stars and DLA galaxies, the 20 DLA galaxies, all have about the same value of their oxygen to iron ratio, and there's something interesting going on at the lowest metallicities, which is a good project for future investigation. Some systems seem to show the nucleosynthesis from early generations of stars, and the properties of these early generations of stars seem to suggest, based on these models, that there's a factor of 2 less energy released from the type 2 supernova explosion compared to what we see in the local universe. These systems are also ideal for trying to measure or pin down what the primordial deuterium abundance is, and that's exactly what we've done for 5 systems. We haven't seen any departures from the standard model, but I just want to close by saying that the most metal-poor DLAs are truly the ideal environments if you want to study anything to do with early nucleosynthesis. So thanks. Ah, right. I see. I think I see your question. Let me know if I've misinterpreted what you're saying. So,
because your error bar is only 0.18, which is considerably smaller than 0.28 when you also include the CMB.
Oh, you're saying you include the CMB here as well. I haven't done that yet. I'm not sure what you can learn from this. I mean, it would pull down the errors a bit more and probably pull down the value a bit more.
What
but
you said was that there's a considerable uncertainty in YP.
Yes.
The primordial abundance of helium. And is that reflected in?
Oh, yes. This is actually this includes the systematic uncertainty, and this is in fact dominated by systematic rather than statistical uncertainty. So this is recently, just in this last week, I think it was a paper on AstroPH this week. This has recently been revised down a little bit from previous analyses, but yeah, this is completely dominated by systematic uncertainties. But yeah, there's a lot that goes into trying to calculate the primordial helium.
The real question is, should we actually take seriously that there's some additional relativistic species in the early universe? That's the 3.57 suggests.
At this stage, I wouldn't personally, just because I mean, really, this is can completely come from the primordial helium mass fraction stuff. So I think the answer is, if you can trust the helium-4 mass fraction stuff, then you have to trust this value. But I'm personally still not skeptical, but concerned about how accurately you can pin down these values from the techniques.
So the new plot of the deuterium abundance is really amazing compared to the previous plot where there's a lot of scatter. Do you want to comment on what, like, you listed a bunch of things that you did, you know, that were supposed to be more accurate on. Is there one thing that dominated? Can you throw out some data points that were problems? Like what caused that to just line up so beautifully?
Okay, so the main reason is I think twofold. First of all, most of the analyses, I think in fact all of the analyses before this, placed the quasar continuum down a priori before fitting. And so what we've done here is we've marginalized over that and included the continuum during the fitting process. So in other words, whatever their uncertainty is in the continuum, that gets folded into the final error on D to H. And so what you're seeing here is that folded error into that. We've also selected the systems such that they're almost guaranteed to produce precise and accurate results for the primordial deuterium abundance. The reason being this, you want to make sure that the system has damping wings to the hydrogen lines, and that means that you can really pin down what the hydrogen column density is. For lower column density systems like Lyman limit systems, there may be some uncertainty in the absolute value of that because you don't have the damping wings to facilitate your measurement. Taken to the other side, you also have a bunch of deuterium lines that are all very weak. And when you're in this weak regime of absorption lines, you're just counting up atoms. And so you get that very accurately as well. So I think it's just due to the selection and also folding in the continuum, the possible uncertainty in the continuum.
So what is the current status for lithium-7? You know, the problem is still there? I mean, you know.
Yes, yeah, the problem is still there. So there was a recent paper that came out on AstroPH maybe a few months ago where the lithium-6 has now gone away. Lithium-7 is still around, and that's still a factor of 3 less than the standard model. There's also a concern that no matter how much you change the physics if you make any sort of non-standard assumptions, it's still very difficult to match up lithium. So something is still strange with lithium. And in fact, we have a project to try and address that with DLAs. So stay tuned and see what we can find.